Traditionally, the instruction of target motion analysis, or TMA, starts in the classroom. For example, this is a depiction of training material for the parameter evaluation, or PEP plot. However, with the advent of virtual world technologies, we can go beyond the passive learning experience and create a more immersive environment where the student and instructors are immersed in the information space itself. For example, if I look at a target motion analysis timeline of 20 minutes, I see 4 depictions of time-bearing plots, where I am first 3 minutes into the scenario, still first ownership leg of the scenario at 9 minutes, and then eventually reaching full observability with 2 ownership legs at 20 minutes. So a fundamental question is, how do you extract a solution from this tactical time-bearing plot? If the operator selects this particular snapshot in the timeline, in virtual space we begin assembling all possible trial solutions that can occur between the most recent line of bearing and the oldest line of bearing, the tie-down bearings, if you will. The solutions are plotted in geospace here, depicting all combinations of range, course, and speed. Furthermore, in the parameter evaluation plot in range versus range space, each of those trial solutions are also in real time being represented as an individual cell. So each square cell in this particular plot represents a unique trial solution with unique range, course, and speed. As each solution is generated, both in parameter evaluation space and geosit space, the solution is evaluated against measurement data. This is depicted best in the traditional difference plots. A vertical representing difference plots, depicted in red, means the dots have been stacked. The measurement bearings match the trial solution well. Those trial solutions that have curvature or are not vertical in general mean that there's large degrees of RMS, or root mean squared error, on the trial solution against the measurement data. This is the testing of each hypothesis against the supporting data that inputs it. Now that the PEP is completed generation, we can go further and actually immerse ourselves into the tactical plot. What we see here is that the sides are not very steep. First of all, this means that the difference in RMS value, the z-axis, between one trial solution and another, and that value is in degrees, for example 1.7 degrees to 2.36 degrees, is relatively moderate, a relatively small slope, meaning there's not much difference in how good the data, the trial solution, fits the actual measurement data. We also see, because of a single ownership leg, that we have a wide band of red, or low RMS value, indicating that there are many trial solutions that still match the data. Now let's jump ahead to the 20-minute mark. At this point, we should have multiple ownership legs of data providing full observability to the geometry. What we would expect to see is a much smaller set of viable trial solutions that have a very good match to the data. As before, we see the geosit trial solutions being rendered in real time. We see the greens and blues indicating some of those solutions right there. And as each solution is being tested, we see the difference plots reacting to the measurement versus trial solution data. Since we are immersed in the environment, we obviously notice a much steeper gradient in comparison of trial solution to trial solution to trial solution. Each step represents a different trial solution, but with slightly different range characteristics: closer, farther, opening, or closing. As we complete this particular PEP plot, we're going to see just a small area of low RMS, or red cells, and we're going to see that it's fully enclosed. If we jump ahead slightly, we see the PEP plot is now complete, and indeed we have the traditional bullseye type of PEP image display, indicating that only a very small subset of the all possible trial solutions indeed have a low RMS value, less than 1 degree. Now, even one cell difference creates a significant change on our difference plot. This trial solution here, depicted by the small hand, is the best indeed fit to the measurement data. Another way of evaluating the goodness of this PEP plot in terms of geometry is to see the gradient measurement. If we allow 4 balls to fall into the PEP plot, they're naturally going to fall to the lowest point, which is indeed the lowest RMS. If we send several groupings of these balls down, basically representing a scatter plot sampling of it, they're going to begin to accumulate along one particular center ridge and eventually along one grouping of best solutions here. How well the balls group is a measurement of the observability of the TMA geometries. In those earlier geometries, where there is very little observability, and indeed it's potentially even just a flat plane 3 minutes into the scenario, the balls would not group at all and would just fall straight down. In conclusion, this experiment was meant to demonstrate the use of virtual world technologies, specifically their application to immersive learning, by putting the student into the information space. Studies have shown that as opposed to passive classroom experiences where they're just observing information, if the student can actually interact with the information and control it, it becomes an experience. And when it becomes an experience, factors such as retention rate increase dramatically. If you'd like more information, you may contact me at the email address below, steven.aguiar@navy.mil. Thank you.